We're moving on from static to current electricity. So in this vid, we're going to talk about electric potential, or voltage, and when a charge moves from one voltage to another, how much energy it gets. And another form of energy that we can use is the electron volt. If you're using your ISM Mike Dickinson packet, you can follow along on pages 1 to 3. So let's talk about the electric potential and the energy charges can get when they move across an electric potential. So let's drag on this statement about electric potential difference. You may take a minute to write this down. Now to help, hopefully you've done that, hopefully to help explain it, let's take a look at this next page. Let's say we've got two plates, and these are going to be like a capacitor. Negative on one side, positive on the other, and these lines in the middle are representing their electrical field, which is uniform in the middle. And let's say we've got a positive charge. It doesn't like being near the other positive plate. So if we were to move it from side A, over to side B, let me show you guys what's going to happen. It's going to take some work to move it from A to B. And work, you know, is force times distance. And that's going to give it some energy. And that's going to be electric potential energy, because it's going to be stored, because it's going to be hanging out near this positive, which it doesn't like to do. And the force that it takes to move us is going to depend on the strength of the electric field times the charge times the distance, which is going to equal this electrical potential energy. Now, if that charge is now hanging out over here, you have to hold it there. If you let it go, zoop, it zips over to the other side. So the amount of energy you're going to get, that's going to be kinetic energy, and that's going to come from your energy potential, that electric potential. So you've got your electrical field times Q times D is equal to kinetic energy, 1/2 mv squared. Let's say you wanted to solve for the velocity. You would just rearrange this, and you'd end up with this kind of crazy equation, which may look weird, but not too hard to work the algebra on that. So here's the actual definition for electrical potential difference. So you can pause it and write this down, but know that this is the same thing as voltage. Voltage and potential, or voltage and potential difference, it's all the same thing. And you want to know that this is in energy per unit charge, or in the units of joules per coulomb. And this is like the potential that you may have already studied of gravitational potential, which is in the units of not joules per coulomb, but joules per kilogram. And you can think of as this is how much energy a charge is going to get as it zips across two plates. Now the electron volt is a type of energy that you will get if you have an electron, and let's say our electron is in between two plates, and if you have it over near the negative end and you let it go, zoop, it's going to zip over to the positive side, and it's going to gain speed. It's going to gain a certain amount of energy. And you can write this down as the definition that the energy it gains is a certain amount that it gets when it goes across 1 volt. And that's a small amount of energy. And so what we say is that 1 electron volt is equal to an energy, tiny energy, of 1.6 times 10 to the negative 19 joules, which is tiny, tiny, tiny. That also happens to be equal to the charge on an electron in coulombs. But what you need to make sure you know is that this is energy. Don't think that it's a voltage or a potential. It's another unit of energy, just like a joule, except much smaller. Here is a sample problem made by Mr. Dickinson. So take a minute and pause it and see if you can solve it. Hopefully you did, or at least had a go at it. And what's going on is we've got these plates with 50 volts across them, and they're only 5 millimeters across, and we have an electron. So let me move to the next page. For part A, if we're trying to find the electric field strength, there's an equation that's not given in the data booklet, but I think it's useful. And that's electric field strength between plates is equal to the voltage divided by the distance between them. So then, if you fill in your 50 volts and you fill in your 5 millimeters, then you get that answer of 1 times 10 to the 4th newtons per coulomb. Remember that for electric field strengths, you should get large numbers. 4. Part B wants to know what the force on the electron is. You should know that an electric field force is the electric field strength times the charge. You take this number and plug it in, times the charge on an electron, and ba-bam, you got your answer of 1.6 times 10 to the negative 15th newtons, which is small, but an electron is small, so that would be enough to make it accelerate. And then part C, the loss of electric potential. Well, that is easy. If an electron is going to lose 1 electron volt of energy as it moves across 1 volt, if it's moving across 50 volts, it gets or loses 50 electron volts. So that answer is just 50 electron volts. And likewise, part D is easy because it's asking how much kinetic energy is it going to gain. Well, whatever potential energy it lost, that's the amount of kinetic energy it's going to gain. So they're the same. And then part E is asking how fast is it going. Here you need to do a conversion. You want to take 50 electron volts and let's convert that into joules. 1 electron volt, as we said earlier in the video, is equal to 1.6 times 10 to the negative 19 joules. And that is going to give you a tiny amount of energy of 8 times 10 to the negative 18 joules. Now you take that energy, that's going to be kinetic, and you set it equal to 1/2 mv squared, and then you solve for v. You fill in the mass of the electron as 9.11 times 10 to the negative 31st kilograms, solve for v, and you're golden.